Hello everyone, good afternoon. My name is Muntaha and I am from University of Applied Sciences. I am working as a junior researcher and today I am here on the behalf of my team to present our report, Flood Level Estimation from Social Media Images. Okay. And so I will start by introducing my team. So Julia actually worked on her internship for this task and we kind of helped her and finalized the task in the end under the supervision of Matthias and Marcus. So Benjamin actually pretty much explained all of my slides. So still I will tell you about the approach and everything. So I will start by showing some examples because I want to tell the challenges which we have. So all the challenges are actually about data. That's why I am repeating data, and data. But the main problem was the data was highly imbalanced. And we have this modality issue, like the visual appearance of water was really different, as you can see from picture 1, 2, 3. The water is really different, the color, and the reflection and occlusion, as he already explained, but I will show you some examples in the next slides. So let's go to the approach. So we use this visual information only, and we proposed a method based on water detector and pose estimator, the combination. And the final result is actually, if we have all of them true, then it means we have a positive example. So for water detector, we use ResNet 50. And the input size is, of course, 227 to 227. This one is pre-trained on ImageNet, and we fine-tuned it for binary classification for water and no water. And the data, so here comes the point that we don't have, so this dataset is actually from the task which we have from 2018, but the problem is we have no annotation, so we annotated the data for this specific task. And then we use pose estimator, and many of you already know the open pose. It gives you the skeleton and the ID. We have the ID of every joint, I would say. And to avoid the false skeleton, like sometimes you have some of them with no upper part, and so for us actually the lower body part is important because the task was actually to at least one person should be in the water. So what we do here, we compute the confidence score for the upper body parts, and the ID is 0, 1. This 0 is our head, and for the chest is 1. And this, for the lower part, we use these IDs 9, 10, 12, and 13. These are actually below our knees. So the rule-based classifier needs these two confidence scores. And this is actually what it's doing is how likely the lower body parts are occluded. If they're occluded, it is good for us. This is what we want. And it should be high for the person if he has some missing toes or foot or something. And the final is, again, if we have water in the image, and if one person is not, or if this is positive, then we say, okay, the final decision is a positive one. So further, we used two approaches. One was global water detector, and the other was local one. In the global one, we use this open pose and a water detector in parallel. And so if something like this, if again we have used this rule-based classifier, and then if the both of the results are positive, we say that our results are positive, and we call them lower extremities, as I explained it here. And we use this for our run 1 and run 4. So the next one is local water detector. What we do here is we apply open pose. As open pose gives you already the body parts or skeleton, we compute the bounding box, and for each bounding box, then we say, okay, if there is a water in this bounding box for this person, then it's positive, and if the lower part is missing, and also a water for each person in the image. We compute this, and the final result is again the combination of water detector and this rule-based classifier. And this is actually, we use this for approach 5. And now you will wonder why we don't have this approach 2 and 3 here. We are directly on the 5 and 4. So the thing is, we were unable to work with this text data. It was highly noisy, I would say. Some links were broken, and we were short in time. So from the results, you can see that this local-based and global-based approach have really, you can see the difference in the validation set. But there is no much difference, I would say, in the test set. But it's also, you can also see that our model generalized really well on the unseen data or the test data. And of how we divided the data here, we actually have this 20% from both classes, and we put it on the side from training set to validate our approach. So here are some insights. What are the strengths of our model? Is actually the generalization ability, as I explained it in our results section. And the water detector actually worked really well. It was like 88%. It was really good. And the limitations were again the reflection in the water. As you see, sometimes the pose detector confuses it with lower torso, or I would say the lower part. And occlusions like this, some cars somewhere, or there are many examples we have in the results. And of course, and these are the problems which leads to the false misdetection by open pose. And what we have for future recommendation, we say, okay, if we do segmentation, maybe we get some better results. Maybe we don't get confused with the reflection or something. And maybe if we use some good algorithm for pose detection, then it could be, yeah, it could get better. So I think I will take questions here.